Good morning, AP Calculus AB. Miss G here. It's Thursday, March 19th. I hope you had a nice day yesterday. It was a pretty day. I hope you got out and had a nice walk or just a little sunshine just to get a breath of fresh air. I hope you're ready to do a little calculus today. So the first thing I have are some questions that people emailed me. And the questions I'm going to address are in section 5.7, page 377, and the questions are 13, 39, 51, and 55. If you got all those questions, you can just skip ahead to my notes today. All right, so let's start with 13. The directions were determine whether y equals x squared is a solution of the differential equation x y prime minus 2y equals x cubed e to the x. All right, so our proposed solution is y equals x squared. Our differential equation with derivatives in it calls for a y prime and a y. Well, we have a y, but we don't have the y prime. So we take the derivative of y equals x squared, and we get y prime is equal to 2x. Okay, well, let's do this step by step. All right, so here's the differential equation. And now I'm just going to substitute in for y prime the derivative of our proposed solution, which is 2x. So we have x times 2x minus 2 times y. Y was originally stated as x squared, so we plug that in for y. And then we simplify it. We get 2x squared minus 2x squared, which gives us 0. 0 clearly does not equal x cubed e to the x. In other words, the left side and the right side have to look exactly the same when you're done with this process. And if they don't, that means that the proposed solution, y equals x squared, is not a solution and it doesn't work. So therefore, y equals x squared is not a solution to the differential equation, this one right here that we've got. Okay, hope you followed that. The next one is to actually solve for the general solution of this differential equation. How do we know it's a differential equation? It says dy dx equals. It doesn't say find dy dx. It says dy dx, which is the derivative, is this expression right here. X times the square root of x minus 3. So we're going to do our process, multiply by dx, get the x's with the dx, which they already are, and there are no y's, so we're all set with the dy on the other side. So now, what do we want to do? We want to integrate both sides. So we're going to need a u du substitution for the right side. So we can let u equal x minus 3, and then the derivative of x minus 3 is just going to be 1 dx. All right, so let's see how our substitution works out here. So x minus 3 is our u. To the 1/2 power, we keep that. We have nothing to substitute in for x, however, because it didn't show up in our du expression. It didn't come out x dx, which would have been nice, x dx, but it didn't. So now we rearrange our relationship between u and x and solve it for x in terms of u. So we just add 3 to u, and we have x is equal to u plus 3. So now we have something to substitute in for x, and that is u plus 3. And now we're going to do a little bit of distributive property before we integrate, which I should have done my little arrows. Boom, boom. Okay, so u to the first power times u to the 1/2 power is u to the 1.5 or u to the 3/2 power, plus 3 times u to the 1/2 is 3u to the 1/2 du. Okay, we didn't integrate anything yet. We're just getting it all set up. Now we can integrate. Integrate the dy, integrating 1 dy with respect to y is y. And so we get y on this side. And then we do our process. Add 1 to 3/2, we get 5/2. Divide the coefficient of 1 by 5/2, we get 2/5. Take 1 and add it to 1/2, we get 3/2. Take 3, divide by 3/2, and what do we get? We get 2. Oops, yeah, we get 2. All right, so let's see what we got out of this process. We got 2/5. Our u is x minus 3. Our exponent is 5/2. 3 divided by 3/2 is the same as 3 times 2/3, which will give us 2. And our u again is x minus 3 to the 3/2 power. Okay, plus c. So In case you can't read that, I think I wrote it again. Here we go. Y equals 2/5 times the quantity x minus 3 to the 5/2 plus 2 times x minus 3 to the 3 halves plus c. And there's the solution to 39. I hope some of you did get that problem out there. All right, let's move on to 51. So 51, it's the square root of 1 minus 4x squared times y prime equals x. There's our derivative y prime. We'll isolate y prime to start. So we just divide by the square root of 1 minus 4x squared. Now we have to change or to rewrite y prime as dy dx. Then we multiply by dx. Again, fortunately for us, we just have all our x's already with dx, and we have no y's like we did yesterday. So we have a little easier situation once we've separated the variables. And now we integrate both sides. So we're going to integrate dy, and then we're going to integrate the expression here. So again, a u du substitution. U 1 minus 4x squared, the derivative of 1 minus 4x squared, derivative of 1, 0, derivative of negative 4x squared, negative 8x dx. Well, the x dx is covered in our du because here's x dx. And our 1 minus 4x squared is our u. So substituting with our u du expressions, we get the integral of dy equals 1 over the square root of u du. But remember, the du here, or note that the du has a negative 8. Well, there's no negative 8 in this problem. So we're going to compensate for the negative 8 that's inherent in our du by multiplying by the reciprocal of negative 8, which is negative 1/8, which essentially cancels out the negative 8 inherent in the du. All right, so now let's see what we've got. We integrate dy, we get y. We have our negative 1/8 coefficient, and now we're going to integrate u to the negative 1/2 du. So we add 1 to the exponent, we get positive 1/2. We divide the coefficient here, 1 by 1/2, we get 2. So now we have negative 1/8 times 2 u to the 1/2 plus c, which simplifies to negative 1/4 times our u, which is 1 minus 4x squared to the 1/2 power plus c. There you go. I hope you followed that okay. That's 51. And moving on to, ooh, look at this one. This one's kind of long. 55. Find the particular equation that satisfies the initial condition. All right, so let's see what we've got. Y times y prime minus e to the x equals 0. So we'll isolate y prime. Y prime equals e to the x. Y prime equals e to the x over y. So all we did was get y prime by itself. Now we're going to rewrite y prime as dy dx. And guess what we're going to do? Multiply by dx. So we multiply by dx, and we're going, oops, we have a y on the side with dx. We need it on the dy side. So we multiply both sides by y, and we get y dy equals e to the x dx. And now we can integrate both sides. So when we integrate y, we get 1/2 y squared. We integrate e to the x, the fun one, and we get e to the x plus c. Today I put c sub 1, but you could just put c. But some people don't like that, so I'll put c plus c sub 1. Now what happens? Now we have to multiply by 2 because we're trying to isolate y. So we multiply by 2. We get y squared equals 2e to the x plus, really, we do get 2 times c sub 1, which just becomes another c, which I could call c sub 2, but I'm just going to call it c. So you don't have, the 2 doesn't have to show up here, but it does have to show up here. So, let's see. Now, if you look in the back of the book, I believe that's what they left for the answer. We could call that our general solution, but now they want a particular solution or particular equation here. And our initial condition that was given in the original statement of the problem is that y of 0 is equal to 4, which tells us that the point 0, 4 is on the graph that we are looking for our particular solution. So I did isolate y by taking the square root of my y here in the general solution, and I get plus or minus the square root of 2e to the x plus c. And now I'm plugging in 0, 4. 4 for y, 0 for x. And I did opt for the positive square root because this square root is either above the x-axis if it's positive or below the x-axis if it's negative. Our point is 0, 4, over 0, up 4. We know this point is above the x-axis, so we opt for the solution with the positive square root because that's where the positive square root would be, and this point needs to land on this graph. All right, so now what is e to the 0? 1. So we get 2 times 1 plus c under the radical equals 4. We need to get rid of the radical, so we square both sides. We get 16, poof, the radical goes away, equals 2 plus c. C now is going to equal 14. All right, so now that is going to go in to, where did I isolate y? Right here, I took the positive one. So y equals the square root of 2e to the x plus c, but now my c is 14. You could have also, in this particular problem, plugged 14 in here. Y squared equals 2e to the x plus 14. That would have worked as well. So we have general solution and particular solution. All right, if you have any questions on this one, you can email me the questions, but I hope you followed that. I think that does it for our problems from last night's homework or yesterday's homework. Now, we're going to do something that's very familiar to you, I hope. We're going to do a little review of inverse functions because we're going to be talking tomorrow about the derivative of the inverse. So before we talk about the derivative of the inverse, we want to review a few concepts about the inverse itself. And this information is on page 332. And this information you learned from Algebra 2 and Pre-Calc, but in your Calc book, it's on page 332 if you want to look up some references. All right, so first thing we start, definition of inverse function. What is that? A function g is the inverse of the function f if f of g of x is equal to x for every x in the domain of g, or g of x is equal to x for each x in the domain of f. Now, I didn't give you one, but I bet you remember from pre-calc, they give you f, they give you g, and you have to simplify f of g of x and show that it comes out to be x. I know you did those kind of problems in pre-calc. All right. And similarly, g of f of x had to come out as x. All right, so these are two things we're going to keep in mind for tomorrow's lesson. Let's see what else we know about inverse functions. So, the notation. The function g is denoted by f inverse. That's not the reciprocal of f. That's not 1 over f. That's f inverse. And that's what we just defined right here. All right. What we learned about inverses from pre-calc. We learned that to find an inverse, remember that? You interchange x and y, and then you solve for y. So I took a really simple one, and let's just take a look at this. So we interchange. So here's our function. F of x equals 2x minus 3. And we know that f of x can be replaced by y. So we have y equals 2x minus 3. If you want the inverse of that function, you put x where y is, y where x is, and that's the first step. And then you solve for y. So I just added 3 and divided by 2 and simplified as y equals 1/2 x plus 3/2. And with inverse function notation, that's saying that f inverse of x is equal to 1/2 x plus 3/2. Okay, now what does this really mean? If we interchange x and y, what should we see? Let's check it out. If we picked points on the original function, -2, plug -2 in here, we get -7 for our y value. -1, we get -5, etc. There's my little chart. That goes with f of x. What happens if I pick points on the inverse function? So now, if I pick -7, I have -7/2 plus 3/2. That's -4/2, which is -2. I'm not going to go through these because the easy way to look at this is we just interchanged x and y. So every x and y over here gets switched. -2, -7 becomes -7, -2 for the inverse. That is a key concept. Well, here it is. What was an x value for f of x becomes a y value for the inverse function, f inverse. Key concept. Keep that in mind for tomorrow's lesson, and let's move on with that. What else do we know about inverses? Oh, well, we know that since the x's and the y's flip-flopped, that means the domain of f is the range of the inverse, and the range of the original function f is the domain of the inverse. Okay, there we go. Next, we talk about one-to-one. A function is one-to-one, meaning that it passes the vertical line test, which is really what makes it a function. And then to be one-to-one, it has to pass the horizontal line test. And if that's true, then the inverse will be a function. So you can take a look at page 334 to see more on that. When you do these problems tonight that ask if the function's one-to-one, take out your calculator if you like and graph it. See if it passes both vertical and horizontal line tests, and you'll know if it's one-to-one. What else do we know? We talk about strictly monotonic. If a function is strictly monotonic on its entire domain, then it's one-to-one and therefore has an inverse function. What does strictly monotonic mean? Well, mono in the English language means one. So this means the function is only doing one thing on its domain. It's either always increasing or always decreasing. And if we can find out whether it's always increasing or always decreasing, and we can determine that it's monotonic, then if it's monotonic, we know that it will have an inverse that's a function. All right, so how do we determine if it's monotonic? Well, if we want to know if something's increasing or decreasing, from way back when in our sign patterns, we take the derivative. We look at a sign pattern. Sometimes we don't even need the sign pattern, as you'll see in the next problem. So here's an example from page 338, number 23. It wants to know if the function given x plus a cubed plus b is strictly monotonic. So let's take the derivative. F prime is chain rule 3, keep the base the same, drop the exponent by 1, take the derivative of the inside function. The derivative of x is 1, a is a numerical value, the derivative of that would be 0. So, and then the derivative of b, which is a numerical value, is 0. So the derivative comes out 3 times the quantity x plus a squared. Now I'd say find the critical numbers and do a sign pattern, but 3 is positive and any quantity squared is positive, which means that the derivative is always positive. And if the derivative is positive, the slopes of the original function are positive, which means that the original function is increasing all the time. Okay, because it's always positive, always greater than 0. Therefore, f is strictly monotonic, always doing one thing, increasing, and therefore has an inverse function. Okay, do we know anything else? Let's see. Determine if the function's one-to-one. Oh, I said you could use a calculator to graph the function and see if it follows the one-to-one definition I just talked about before. Okay, next. Let's take a look at this function and see if we can find its inverse. So y equals x cubed. And then I found the inverse. Y equals x cubed, interchange x and y, x equals y cubed, solve for y, take the cube root of both sides, y equals the cube root of x. All right, and so then I did the point thing again. I picked some points, plugged them in to x for the original function. There are my y's, and then I know if this is the inverse, those points are going to flip-flop. The x becomes the y becomes the x, or the domain becomes the range becomes the domain. They switch. So you can see my two charts right here. All right, now I graphed it. So we could take a look at it for our last concept about inverses. So I graphed y equals x cubed, that's the blue one, and the purple one is the y equals the cube root of x. And you can see there's 2, 8, there's 8, 2, there's negative 8, negative 2, there's negative 2, negative 8. And what we see is if we draw the line, the dashed line there, y equals x, these functions are reflected over the line y equals x. Not surprising, because we interchanged x and y, and we can see that if we folded the paper over that line, this piece would be superimposed over that piece, and this piece would be superimposed over that piece. So they are reflections of each other over the line y equals x. All right, so now I'm leaving you in suspense because we need all that background information for tomorrow's lesson when we look at the derivative of the inverse function. All right, so I hope you processed this. I hope some of it was familiar. And surprise, surprise, we have a little practice tonight. And that is section 5.3. And I know that that's a section a while ago that we didn't cover. We skipped it. So now we're going back to it. Page 338, 339. These are the problems. They're pretty much the same problems as the ones on your homework assignment sheet for section 5.3. I think I took out one problem, 45 or something, but this is good. All right, this is all pre-calc and Algebra 2 review, so smile when you do it. And I hope you have a great day. Take care.